Hi, NA Physics, it's Mr. Neff. Today, let's talk about the conservation of energy example problems. And before we do you know where polar bears vote? I'll tell you about them at the end of the video. I got a few examples here that they get gradually more difficult as you go. I'm going to pose the question, and then I'm going to ask you to pause the video each time to see if you can come up with something on your own. And then after you've thought it out for a little bit, come back and see how our work compares. Look at this number 24. It says a skier slides horizontally along the snow for a distance of 21 meters before coming to rest. They're not pushing, they're not using their poles or anything like that. They're just sliding horizontally along the snow. Maybe they start off right there and they end up right here at rest. They were going at a certain speed that they want you to calculate. So we're looking for this speed right here. And they do tell you that they went 21 meters in coming to rest. Now it's friction that is the worker here. And so there it is. Now you were able to do this problem when you only knew the basic version of the work energy theorem, but you can also use the work non-conservative version of the work energy theorem too. That's the solution that I'm going to show. So my first step is going to be work non-conservative plus kinetic energy initial plus gravitational potential energy initial plus spring potential energy initial equals kinetic energy final plus gravitational potential energy final plus spring potential energy final. Now, a lot of those terms are going to cancel out to zero. You decide which ones, and then you substitute in and see if you can get that initial velocity. All right, and we're back. Now, the right side of this equation is actually going to turn into all zeros. There are no springs in this problem, and so both of the spring terms turn into zero. There is no change in height, and in a case like that, what you want to think of is the height that you're on is the height equals zero, which then when you go mgh, but you put a zero in for the h, then that term turns into zero. And we're going to be stopped at the end as well. And so the kinetic energy final is going to be zero because the final velocity is zero. So really, this just becomes the work non-conservative is the change in initial plus the initial kinetic energy is equal to zero. Now the non-conservative work is going to be the work from friction. So I'm going to call that the work from the force of friction kinetic, and that's equal to the negative of the initial kinetic energy, 1/2 the mass times the initial velocity squared. Negative because it went to the other side of the equation. So as complicated as that looked at first, now it's gone down to something pretty basic. Now the work from a force is the force itself times the displacement times the cosine of the angle in between the force and the displacement. The friction is going to act backwards on this skier, and so this is going to be the cosine of 180 degrees, which will be negative, which would be nice because it'll cancel out that negative on the other side. The force of friction itself is the coefficient of friction times the normal force, and then the displacement. That's equal to -1/2 the mass times the initial velocity squared. Look at what I have. I'm going to have a 0.050 times the normal force. Now, how big is that normal force? Well, that normal force is the same size as the force of gravity, so it is equal to mg, and so it is m times 9.8, and the displacement was 21 meters, and cosine of 180 degrees makes the thing negative. That's equal to 1/2 the mass times the initial velocity squared. Now, when you were solving yourself, I'll bet you noticed that they didn't give you the mass, and some people probably thought that that was a problem. Well, it is not, because the masses are going to cancel on both sides, which is not just a nice thing in this problem, but it shows that this outcome, it doesn't depend on a mass. So this would be good for a little kid, this would be good for an adult, this would be good for whatever. And so all you have to do then is multiply 2 times the, oh, and the negatives are going to cancel each other out too. I had this initially there. 2 times 0.050 times 9.8 times 21, and then I'm going to take the square root of all that. It ends up being the square root of 20.58 meters squared per second squared, and then that's what the initial velocity squared is. So the initial velocity itself is 4.5 meters per second. There you go. I hope you got that right. Now, let's look at an example that's just a little bit harder. Look at this one. Here we have an extreme skier starting from rest, coasts down a mountain slope that makes an angle of 25 degrees with the horizontal. Coefficient of kinetic friction between her skis and the snow is 0.2. She coasts down a distance of 10.4 meters before coming to the edge of a cliff. Let me sketch that before we go too much farther. So we're going to come down like this, 25 degrees like that. She's going to start off here, and she's going to coast down this way. And we have a bunch of forces acting now. Now we have the force of gravity X, if you remember your stuff about inclines, and we have friction. So the force of gravity, even the X component, is a conservative force. And our new work energy theorem equation doesn't include any conservative forces. Those are in there as in the form of gravitational potential energy. So you're going to like that. So then if you read on, it says, without slowing down, she skis off the cliff and lands downhill at a point whose vertical distance is 4.3 meters below the edge. So she comes off the cliff and she ends up landing down here. And I don't really know, where she's going to come off at this angle. This is what her initial velocity in the air is going to look like. But then she's going to start curving like this, and she's going to end up at a spot down here like this. And so you see what we have here. We have kind of spot 1, spot 2, and spot 3. And what you're going to see is the energy between spot 2 and 3 would be the same, because the only thing acting is a conservative force of gravity. Energy between spot 1 and 2 is not going to be the same. There's a non-conservative force occurring there, and so the energy at 2 is actually going to be a little bit less than the energy was at 1. At 1, she had gravitational potential energy, and she was starting from rest, so that was the only kind of energy she had. Then at 2, she had gravitational potential energy. If it's okay, I'll call it gravitational potential energy 2. And she also had kinetic energy. I'll call that kinetic energy 2. And now at 3, this is the lowest point in the problem. And you're going to notice something that I like to do is I like to say that the lowest point in the problem is height equals 0. And so because of that, she only has kinetic energy. I'll call it kinetic energy 3. And so there you have it. I'm going to say that the amount of energy that she has at 1, the total, like sometimes I like to just refer to that as E, energy, mechanical energy. At 1, and then you have the energy at 2, and then you have the energy at 3. Well, how do those relate to each other? Well, the energy at 1 is going to be more than the energy at 2 because there was some friction that did negative, non-conservative work between 1 and 2. But then 2 and 3, the only force that's acting is a conservative force, and this would be equal. One more thing before we start the actual problem is if this was frictionless, then the energy at 1 and the energy at 2 and the energy at 3 would be all the same because there'd be no non-conservative forces. They would look differently. Sometimes it would be potential, sometimes it's potential and kinetic, sometimes it's only kinetic, but they would have all been the same without that friction in there. Okay, so they want to know how fast she's going. So this velocity down here, we'll call it velocity 3 just before she lands. Now, what I would say we do here is we look at spot 1 as our initial position and spot 3 as our final position. And well, you say, what about spot 2? Well, spot 2 is important because it ends where the non-conservative work is happening, but in terms of initial and final, I'm not going to include it. Okay, so I'm going to do something like what I did on the last one. I'm going to say that kinetic energy at spot 1 plus gravitational potential energy at spot 1 plus spring potential energy at spot 1, which you know is going to cancel out to 0, plus work non-conservative equals those same things at 2. Kinetic at 2, at 3. Potential energy at 3 and spring energy at 3. There's no springs in this problem, so that's going to cancel out. All right, so what I'd like you to do now is I would like you to stop the video. I'd like you to cancel out as many of those terms as R0 and see if you can make some progress in getting that velocity 3. It's in this kinetic energy 3 term. See if you can get it out. Pause the video. I'll see you in a little bit. All right, everybody, we are back. Let's take a look here. She's not moving at the start, so I'm going to cross off this kinetic energy 1. There's no springs in this problem, so that's going to go away right there. At the end, I'm calling that height equals 0, so there's no gravitational potential energy at spot 3. There's no spring energy in this whole problem. And so what do I have? I have gravitational potential at 1, and just so we're not, that was initial, but I'm going to just put a 1 there so everybody knows that I'm talking about that spot at the way top. That's equal, plus any non-conservative work, which is going to be negative, and that's going to be equal to the kinetic energy final, and that's going to have that velocity in it. Okay, so now how much potential energy does she have? Well, mgh. Now that h is the h above height equals 0. So that's in 2 bits in this problem, yeah? It says that this part right here is 3.5 meters up. And then there's also this part right here. Hey, look at what I'm drawing there. It told you that she slides down 10.4 meters. So do you see something? Do you see that this height right here is 10.4 meters sine of 25 degrees? And if you do that, you end up getting 4.395 meters. So it looks like that's a total of 7.895 meters. So all of this, all the way down, 7.895 meters is how much height she ends up losing. Okay, so we have that. Then we have this work non-conservative. Now the non-conservative work is the work from friction. And so that's going to be that force of friction times the displacement times the cosine of the angle in between the tails. Now that force of friction, let's do that over here. Coefficient of force of friction, coefficient of friction times normal. We know on an incline, the normal is the mg cosine theta. Okay. Now, careful, we got 2 thetas here. When we do normal on an incline, that theta refers to the angle at the bottom of the incline. So, versus the cosine of theta in a work equation refers to the angle between the tails, which is going to be different here. Coefficient is going to be 0.2. I don't know the m, 9.8 for the little g, and cosine of 25 degrees. All this is going to come out to an expression for m, which is 1.776 m. There we go. Now, that is going to get multiplied by the displacement. So 1.776 m times the displacement of 10.4 times the cosine of 180 degrees. And we know that's going to be -1. That'll be equal to 1/2 the mass times the velocity 3 squared. Now look at this. There's a mass in every one of those terms, and it cancels out, which is good because they did not give us the mass. And so now, all I have to do is plug in. When I do, this whole side on the left will come out to 59.7826. That's equal to the 1/2. Multiply that by 2 and take a square root. And we're going to end up with a velocity of 10.9 meters per second. Okay, not bad. And with a little more practice, you'll be feeling good about these kinds of problems. Hey, before we go, where do polar bears vote? The North Pole. See ya.